I guess it's time for us to get started, and yeah, we're on to lesson 4 for this week, looking at the advection equation and how we can apply it. We'll see kind of, I think, a nice example with the exercise this week of the advection equation. And although it might sound like something kind of, abstract, hopefully you find with the exercise that it's kind of a useful thing to be able to understand how to use. Before we go into the stuff for this lesson number 4, are there questions about exercise 3, like anything kind of general? So if there's specific questions, we can maybe still give you some help once we finish up with the lecture and introduction to this week's exercise. But yeah, any issues with this exercise 3? No. Okay. So then like last week, we're going to start out with a little lecture to kind of introduce the advection equation and how it's used. And then there are, again, similarly, some notes, for instance, here on the course page about how to solve, in this case, the advection diffusion equation. So it's not quite the same example that we'll use in the exercise for this week. But if you're curious just about how to solve the equation for one example, you can follow through that there. I'm not going to really go through it at all because it's not directly related to our exercise. And then we'll look at exercise 4 as usual. At the moment, I think all of these things are, like, the exercise is still not visible to you yet, and the course page is not yet visible. I'll make that so once we finish with the introductory lecture stuff. I'm kind of hoping we'll take a quick look at the exercise while we do the lecture, just to make sure there's not any typos, because I was trying to make some changes that ended up taking quite a bit more time than I expected. So that's part of the reason why I'm a bit behind. But let's start here with our lecture topic for today, and this is about the advection equation as mentioned. And we're going to look at an example related to river incision. So rivers incising into bedrock can be modeled using the advection equation, and that's what we'll explore. So there's kind of 2 main points. First is just to introduce the advection equation, what it is, and a bit of how it works. And then we'll look at our application here to bedrock river erosion. So to start, though, I don't know, maybe some of you aren't really familiar with what the term advection actually means. This is an example of advection, in this case, of heat. So this is just showing a kind of upper mantle scale geodynamic model where you can see relatively warm material forming at the core mantle boundary and occasionally upwelling. It's mainly happening over here at the edges of the model. And you'll see occasional sort of subduction or downwelling in the mantle of cold material that sinks downward. So in this case, advection refers to the physical transport of some kind of quantity. Here it's heat. So when rock in this case is convecting, as it moves along, it carries with it the heat that it has, so that when rock comes from the surface where it's relatively cold and sinks down into the interior of the earth, it takes that relatively cold material down into the lower part of the mantle, and you see these kind of temperature anomalies wherever you have subduction type behavior or upwelling. You see just the opposite. And in this case, because the sinking or rise of material is fast enough, it carries with it the heat that will then gradually diffuse away once the material sort of stops moving. And you can see that in places where things sink down, and if you see, there's a good example over here, I think coming up, where this sort of sinks down to the bottom, and then you see this blob sort of gradually warm up as it stops moving and kind of comes back to being the average temperature in the mantle. So that's the concept here. Last week was diffusion, and with advection, we're just talking about a slightly different thing. Here, we're just physically transporting some quantity. Mathematically, the two look, yeah.
So what's the advection
Well, so when we looked at the diffusion equation, it combined a couple different parts. One was that we had some kind of rate of transport that was in proportion to a gradient. So in the case of like heat conduction, the higher the difference in temperature is between two objects, the faster the rate of heat transfer would occur at the interface. And it was also a conservation of energy or conservation of mass type equation, depending on what you've applied it to. Advection, in this case, is just referring to the physical transport of heat. So if there was no conduction, I mean, unfortunately, this model involves both advection and conduction, or advection and diffusion, if we want to use the same terms. If there was no heat diffusion in the model, when these cold things sink down into the lower parts of the model, they would just stay cold. So it's just the transport of the temperature of some material at whatever temperature it is at. So well, I mean, if you imagine like if you could go outside and not get cold on a day like today, you could walk yourself around and carry with you the heat inside your body. But of course, when your skin is exposed to the surface, there is heat exchange happening there, so you cool down as a result. But the process of just moving that heat around or moving some mass around is what advection refers to. And again, it'll get a little bit more clear. We can just start with a kind of general comparison to the diffusion equation. So we saw this last week, and these were the two pieces that I just mentioned. One about this flux being proportional to some kind of gradient. We looked at this in terms of these hill slope shapes, these nice curved, diffusive hill slopes, where the flux of mass was proportional to the gradient of the surface. And then there was this other component, this conservation of mass component. And you put those two things together, you end up with the diffusion equation that looks like this in terms of its form, where the rate of change of elevation in this case is proportional to the second derivative of elevation. So that's not necessarily so important for today, but just to kind of remind you what that diffusion equation looks like. When we compare it to the advection equation, they actually look kind of similar. So if we wanted to simulate the same kind of problem, something about changing elevation at the Earth's surface, we can say dH dt over on the left side, change in height over time. And for the advection equation, it's just equal to some constant c times the gradient in the topography, for instance. So dH dx, change in elevation over some horizontal distance x. So first derivative rather than second derivative, and you'll see that these things behave differently as a result of their kind of general form. So the big differences to highlight here is that the change in mass with time is now proportional to the gradient. So first derivative of h instead of the second derivative, like it was for the diffusion equation. And in this case, we have some constant here that has units of length over time rather than length squared over time. So we didn't talk really about what the units were for diffusivity, but it's usually, in the case of something like this hill slope diffusion problem, it would be something like meters squared per second or something similar. For advection, we'll have something that's like in just meters per second. Makes sense because we only have a first derivative instead of a second derivative. So, and we can kind of see the difference in how these things behave with a nice little example here. So if you consider here a channel profile, do you know what that means when I say like a river channel profile? Do you have a sense of what, like, get a picture in your head of what that looks like? Or, yeah, like if we just took a cross section through some river flowing down a hill slope, it might start up here near high elevation, flow, and then go over some sort of steeper part of the river channel and then flattens out again. If we had that river flowing in a case where diffusion was the main erosion mechanism, and there are some types of rivers that would follow sort of diffusion-like behavior, at some period of time, one, we allow water to flow through the river, and what's going to happen under diffusion is that the steep parts, the places where we have changes in the slope of the river, like here, are going to show a change in their elevation. Same thing happens here where it sort of goes from steep to flat. What happens is that gradient becomes more gradual over time as a result of diffusion. And if you let it go for yet another time, what you eventually would end up with is a pretty much a flat or constant gradient for that river in the case of diffusion. Essentially what we'd like to have happen when diffusion's active is that it basically just gets rid of any kind of changes in the elevation. So things get smoothed out here for diffusion. We can look at the same picture for advection. So starting basically with the same geometry that we had before at time 1. And the difference here is that all we do is basically just shift the shape of the river laterally with time. It just moves off, keeping its shape as it goes from here on the right side to the left. So rather than getting smoothed out, it's just being transported laterally. Shape is not changing here in a case where all we're doing is advection. So you can think about this also in terms of heat transport if you wanted to. Same kind of process happens. But the general idea here is that we're just laterally moving this river off to the left. So you can imagine that this is sort of like having something like a plateau up here and the river flowing down the side of the plateau towards some lower elevation. What happens in natural systems if their bedrock channels is not exactly like this, but it's similar enough, that what you do is basically the river gradually cuts its way into the plateau and just migrates into the plateau, keeping sort of the same general shape. We'll see a little bit more useful example of the advection equation for rivers in just a moment. But does the concept make sense? The kind of idea here. I mean, I know that, again, probably most of you haven't had like a geomorphology kind of course, but rivers that are full of sediment versus bedrock rivers behave quite a bit differently in terms of how they change their shape over time. So again, this is our diffusion law, this rate of erosion being proportional to the change in the slope of the river. So that's why the places where the slope changes show you the biggest change in elevation. For advection, the rate of erosion is directly proportional to the gradient of the hill slope. And I'll show you how that works in just a second. The other key thing here is that we don't conserve mass. So if you started out with some kind of fixed box where you had this kind of river model running, anything that is taken out of eroded out of the landscape is just gone, and we don't worry about that for the advection equation, at least not the way that we formulated it here. So there's no kind of built-in conservation of mass, conservation of energy, conservation of whatever in this particular equation. So about this thing where the elevation changes directly proportional to the surface slope, we can look at this with a sort of even more idealized example of a bedrock river. So here we have really a proper plateau, then a fixed constant slope that the river flows over, and then it gets flat again. In this case, if you're out here in some place where at some initial time, so this dashed line is after some amount of erosion, the gray line is at some starting time. If you're out here in some place where the river channel is flat, and we say that the change in elevation is directly proportional to the surface slope, what's the slope here? Yeah, so the surface doesn't change elevation. But if you go to places where there is some slope, the slope is going to be something that's not zero here. And what you see is that after some time, that surface has moved down. Now, what it looks like if you go through a series of these things over time, it looks like the river is just moving this direction at some velocity that's proportional to this, this displacement factor C. So if you drew this over time, the same shape would just go here, then here, then here, and it just moved off to the left. But every time, the same thing works. At places where you have some change in elevation, it's because the slope exists there. Now, if you go here, you can say, well, this is flat here. How come the elevation changes? The idea is that if you go to each place along here and you do this over time, that's how you can go from this shape to the dashed blue shape there. So you don't necessarily do this in one step like I've drawn here, but I've just shown a couple. So yeah, again, this is the kind of thing to keep in mind. Elevation is going to change wherever there's a slope. The slope is flat, the elevation is not going to change. So then, and you can also kind of get a sense of how much this dH and C times dt would be. As this dt goes to 0, that's how you can sort of get around this problem of being at the place where the slope changes and still having an elevation change. But don't worry about that for right now. So anyway, this is kind of an interesting equation to play with. It's a bit like the wave equation. If anybody's done anything with seismology, that's somewhat like an advection equation. The thing is that this kind of behavior that I've shown here is not really that common in nature. Like, you don't go out and find rivers that do something like what's shown here very often. And there's a reason for that. So what happens in natural rivers is that we basically do have bedrock erosion that we can model with an advection equation, but the difference is this coefficient that's here called C isn't constant in nature. And I'll show you why that is in just a moment. And because that's not constant, that changes the shape of the river and it makes it look a little different than the picture we've been looking at. But in cases like this is a nice kind of picture of a, well, this is really like a waterfall in a bedrock river, but basically you've got water flowing directly over the bedrock here. There's not much sediment that's protecting the bedrock from being eroded, and so this would be one place where we could apply this advection equation. If you go places like this is a nice set of braided channels that are far away from where the mountains are in this case, where there's a ton of sediment and not much water to move that sediment. And here, this bedrock erosion isn't really happening because there's so much sediment in the river. It's protecting the bedrock from being eroded. And because of this, we couldn't really use this bedrock erosion equation or the advection equation that I'm going to show for something like this. So it depends a little bit on where you are, which one of these erosion laws you can apply. But if we're someplace like this where it's steep, where the river has carved a nice channel into the bedrock, formed a nice steep gorge at high elevation, then we can certainly use this advection type of equation. So the example we saw before of this channel that's migrating to the left from time 1 to time 3 is if we assume that the advection coefficient C is a constant. And I've mentioned that that's not the case in nature. So why might that be that this, like what might prevent something like a river from migrating at a constant rate? In this case, if the advection coefficient is constant, then the river just keeps its shape and migrates, infinitely across the landscape. So if you imagine this is a natural landscape where there's, some kind of flat or somewhat flat surface, and then a steeper slope and a flat surface, what might prevent a natural river system from behaving this way? Do you have any ideas? Yeah, so that's one good kind of thing to consider here, is that the amount of water that's in the river is different in different places. So if it's eroding, And we said, well, the erosion is proportional to some, just to the steepness of the slope. Well, it's the steepness of the slope plus the amount of water that's there, because if there's no water in the river, it doesn't matter if the slope is steep. It's not going to do any erosion. So that's a good, at least one good example. Is there anything else you can think of in natural rivers that might be important in terms of how fast they erode? So if we've got the water in there and the steepness, we know the steepness is going to matter. Yeah.
I can imagine that the erosion is much stronger the lower you go down the slope.
Yeah, so it could be. I mean, it's as you get more and more water in the river, as long as you keep the slope steeper, then you should basically continue to make the erosion more and more efficient. So if the slope, if it goes flat, then you're going to lose a bit of that erosion power because the water is going to slow down once it stops being moved by gravity. But yeah, that's another good thing to consider. Anything else you can think of that might be important for kind of real bedrock rivers? Yeah. Yeah, right? So it depends what the water's flowing over. If it's flowing over some really easily erodible bedrock, if you've got rivers flowing over limestone instead of flowing over granite, they're going to erode differently. So in nature, there's actually quite a number of things that will go into this, this constant. We got discharge, that's basically the amount of water that's there, the slope, and the bedrock strength. So we pretty much hit all of the main things that are here. All three of these factors will play a role in nature, especially because in natural rivers, as you go up higher and higher in elevation, you generally lose the water. And so that's why at high elevations, the topography is high, because you don't have any water to do much erosion. So, and of course, these things aren't going to be constant in nature. And that's pretty easy to see just in general. So rather than using this kind of form of the advection equation we're looking at, where we have dH dt equal to some constant c times the slope, we're going to use something a little bit different. And that little bit different thing looks like the equation below here, where we say that this constant out in front is something that is spatially variable. This form of the equation, we have a few things out in front of the dH dx term. There's Kf, which is the material properties of bedrock erodibility, so how easy it is to erode the bedrock. Here, W is channel width. So generally speaking, the wider you make a river channel, it will change how it erodes. And then discharge, Q, will also play a role. So if you make a really narrow channel and keep the discharge high, you get a very efficient erosional agent. And if you take that same channel and make it very wide, its rate of erosion might go down. But that's the kind of general picture that might work better for natural rivers, because it takes into account some of the things that do vary in nature. And this is what's known as the stream power erosion model. And perhaps you've heard of the stream power model before. Again, it's applied to bedrock rivers. Now, one thing that's pretty common to do with this stream power erosion model is to make a couple simplifications. One thing that's a little bit difficult to do in using a simple model of something like bedrock erosion is estimate the discharge. In nature, discharge is a function of how big the area is upstream where you're catching the water, and how much rain is falling, or how much precipitation or ice melting or whatever. It gets to be pretty complicated in natural rivers. So what happens more often than not is that in place of Q for the discharge, we just put in something that says, let's estimate that the discharge goes up in proportion to the area upstream of any point in the river. So if you're way downstream, the area upstream would be very big. If you're up at a high elevation, the area upstream would be pretty small, which means the discharge would also be pretty small at high elevation and big at low elevation. In addition, instead of worrying about this bedrock erodibility factor and the width, those things are both just lumped together into one constant called capital K in this case. It's sometimes called an erosional efficiency factor, and it's basically a garbage can. So everything we don't understand gets lumped in here. So here comes lithology, climate, channel geometry, sediment supply. Basically all the complicated stuff gets dumped into the one constant here, and this constant is something that will vary basically every place you would want to apply this, this erosion law, because of course climate will vary, lithology will vary, and many of these different factors will have an impact on how easily the river can erode. The other thing is dH dx is just replaced by S. And it's only to simplify the look of this equation, really, because S is still the slope. It's just the same gradient we had before. It's just given a different letter. And then these things are raised up to power. So A goes to some power m, S goes to some power n. And these are values that are determined from using this equation in natural rivers. So the values of m and n are kind of determined from how real landscapes seem to work. So that's this stream power erosion law, a little bit different formulation. Another thing we could do to even simplify this further is just put in some way of estimating the area just as a function of the distance from the drainage divide. So there's a lot of different ways in which you can do this as well, but like one kind of popular method is just to take the distance and multiply or raise that distance to the 5/3 power. It gives you approximately this sort of estimate of how the drainage area would change as you go downstream. Does that make sense what this is doing, this area estimate? I mean, I could maybe, I don't know if I gave away all the chalk last week. Thought I had one piece of chalk here still. But if we're without chalk, then I won't be drawing anything on the board, but yeah. Well, the point is, if we look at some river profile and we start at the point that's like the high elevation, the drainage divide. So from that point, we have basically zero distance to the drainage divide because we're at the drainage divide, and the area upstream at that point is zero. As you go downstream and get further from the divide, you can estimate how big the area would be just as whatever distance you are away from the divide raised to the 5/3 power. That's an empirical thing just based on the shape of real drainage basins, and of course this again would also possibly change depending where you want to use this equation. Okay, so time to check in and see how well you guys have picked up on how this stream power erosion equation works. So if we look at this equation, it looks something like this. What kind of shape do you think that a natural river channel is going to take from an equation like this? And we can make a couple assumptions. If we assume, for instance, that we're at steady state, which means that the, here in this scenario, I've added in a term U that would be like the landscape uplift or the rock uplift. If that's balanced by erosion by the rivers, that would mean that this shape of the river channel profile isn't changing through time. So let's assume that, just because it'll make it easier to kind of come up with what the shape of this river channel would look like. And let's assume precipitation's constant, bedrock erodibility is constant. Let's not worry about anything complicated, and the area is just x to the 5/3 power. Yeah, what would this thing look like? What would this sort of shape be? How would the channel steepness change as you go downstream if we assume that the uplift is constant and it's balanced by river erosion everywhere? And you can feel free to talk with your neighbor for a second if you've got any idea about this, and we can check in just a moment. So, any ideas what would this river channel profile look like? How would its steepness change as you go downstream? Yeah.
Would it be flat?
It won't be flat. So why would it reduce in steepness as you go downstream? I mean, that's right, but what in our equation would make it so that if we want to balance uplift with a constant rate of erosion, we have to have the river channel get less steep as it goes downstream? Yeah, right?
The change in K is steady, so we have to change S as a bit smaller. It's,
yeah, exactly. So if these are things, if everything's in balance, if K doesn't change, which, okay, in nature it does, but if K doesn't change in our problem here, as you go downstream, the area that, basically how much water you're collecting gets bigger and bigger and bigger. And if the river is meant to be eroding at a constant rate, that means the slope has to get shallower in order to offset the fact that the drainage area is getting bigger or that you're getting more water in the river. So what we would expect then is this kind of shape where it's steep up at the high elevations and it gets shallower as you go downstream, which actually looks a lot like real rivers. And if you use this model and apply it like we will in the exercise this week, that's exactly what we see. We can start out, for instance, with something where there is a constant slope, and it will evolve so that it gets relatively shallow gradient at low elevations and steep up high. And that steepness up high is because there's not very much water, so you've got to make the water flow fast in order to make it erode. As you go downstream, the amount of water in the river goes up, and if it balances then the tectonic uplift, the idea is that it then flows over a much more gradual or shallower gradient for the river channel. So you'll get an opportunity to play around with this stuff in the exercise this week, and we won't really do that much with the stream power model that I'm giving you. So I would say you're more than welcome if you want to play around with it more than what we do in the exercise, because it can do a lot of things and it's pretty interesting to play with, but there's only so much we can do in one exercise. So yeah, we're going to skip these kind of recap questions because I don't feel like doing them. Are there any questions about this advection equation stuff? No. Is the kind of picture of this stream power erosion model sort of becoming more clear? Does it make sense how it works? I mean, again, when you play with it with the code, usually to me at least, that's when I kind of feel like I start to actually understand what it's doing. But it doesn't have to be crystal clear right now, so don't worry about that. So we've done the lecture stuff. Like I said, I'm going to skip over showing you the notes on solving the advection diffusion equation. That's kind of just stuff that's there from years past. And if you're really interested and you want to know how to solve the advection equation for a heat transfer problem, that is there, and you're certainly welcome to have a look and see how things work. Now, if we go to exercise number 4, again, it's still kind of hidden. So Lotta pointed out a few minor things that I'm going to fix before I make it visible to you. But what we can do is I'll just zoom in here a little bit, and we can have a quick look at what the exercise is all about. And yeah, we're going to deal with river advection. I don't know how that should be fixed, but it didn't get fixed. And river advection in this case means we're going to play with the stream power erosion law. And there's one notebook And the link actually points to the wrong one right now. So I'm going to click this and then hopefully this works. So in our one notebook, there's 2 problems and several parts for each problem. In using this stream power erosion law, there's actually quite a bit of code that you need to deal with in order to get it to work. I'm going to have you produce a little bit of that code, and then I'm going to give you a bunch of other stuff. And the other stuff I'm giving to you, my only request is that you take a little bit of time just to read through some of these other functions and things that you're able to use, just to try to make sure that you understand a little bit of what the functions do, because you won't necessarily need to make changes to that much of the functions, but you will need to modify things in a couple places, and it'd be helpful if you take the time just to read through the code and the comments to try to make sure that you have a sense of what the function does. Keeping in mind the idea that one function is supposed to do one thing in most of these cases. So anyway, to start out with the river profile erosion, river profile evolution part of the exercise in problem 1, the first thing you're going to do is you're going to create a new function called drainage area. And the drainage area function basically uses this equation to calculate what the area is of the river upstream from any point in the river profile. So a little bit different than this like x to the 5/3 power, but it's pretty similar. There's just a constant out in front, and then it's raised to some power that's not quite 5/3, but a little bit different number there. But it just allows us to estimate, as you go downstream, how big does the drainage area get for any given point. So that's the equation, and you're given the starting bit of a function. So you can see there's a few different things that are going to be passed into the function. Of course, x in this case is the distance along the river profile from the drainage divide. So it starts at 0 at the drainage divide and goes downstream. And then Ka is the constant Ka in the area equation here, and Ha is the other constant. In this particular case, I've given you values in the definition of the function, and those are fine to use. You don't need to change that. This is just to kind of show an example that you can define values that are in a function that are basically constants or default values. In creating the function, you can define those. So what you'll have to do basically is just put in some code here to calculate what the area is using this equation, and you have most of the pieces there to do that. And I've given a little bit more detailed comment here in the doc string and the sort of description of what the function does, just so that you know what each one of these things is supposed to represent in the function. So that'll be the first thing, and then you're given again like the tests in the past. Some example here where like this test should work, right? So when you run this, I give some dummy list of values of x from 0 to 3, and then it says drainage area at index 3 should be this, and then when you run your code, you should see that if everything is working right in your drainage area calculation, you should get back that value at index 3. So that's what this little print statement is supposed to do. We're just in GitHub, so I can't test that right here to show you. So part number 2, we've got another equation here. So this is the stream power equation. dHdt equals K, A to the M, S to the N. So this is the one that we just saw in the lecture stuff. And your next task is to create another function, in this case called calculate dH dt. And in the calculate dH dt function, you have to solve this equation to calculate the value of dH dt. So this should basically be what the value of the stream power erosion equation is at every distance along your river profile. So you've calculated the area in the last part, and now you can use that area here to calculate the stream power erosion. Again, there are things that are passed in here, and I guess I did not set constant values here, but I could do that maybe before I make the exercise link for the GitHub Classroom thing. Maybe I'll add in some constant values or default values here just so you have those. But again, you've got the sort of general shape of the function here. It's going to take in the topography in this case, which is the elevation of the river channel, the spacing between the points, the area upstream, and then these constants that go into the stream power erosion equation, K, M, and N. So this looks relatively simple. It's a little bit trickier than you might think because you have to calculate the slope. So I'll add a hint in the hints for the exercise this week about how to calculate the slope. I will tell you that the code is a little bit fussy about how you calculate slopes, and it will blow up if you do it the wrong way. So I spent like the better part of a day trying to figure out if I could get the slope calculated some easier way, and I never got it to work. So maybe somebody smarter than me could figure out a way to do that, but at least with what I was given, I found one way that works, and I'm going to put that in the hints so that you can hopefully follow a similar path. I'll tell you that when it doesn't work, it will be very clear it's not working. So your plots will just be a total mess. So that's what you're going to calculate stream power erosion next. And then you get to the bit where I'm going to give you some other pieces of code to use to be able to do the stream power erosion model and to use the stream power erosion law or erosion equation. So there's some pieces here where like I basically just list some different functions and tell you what they do. This is the stuff where I would like you to read through it and just make sure you have a general idea of what these different functions do. So like there's one here called init topography. It's supposed to define the initial shape of the river profile. And there's some different options for how you do that. So you can look through there, and I think this one's not too bad to kind of understand what it's doing, and its purpose is, I think, also relatively clear. Now, the next two are maybe a little bit more challenging to understand. Unfortunately, the formatting looks kind of messy here too because it's wrapped the lines. But there's another function here called update topo. It updates the topography or updates the elevations of the river channel. In this one, the idea is that you call this calculate dH dt function. So this is the one that's going to give you the stream power erosion rates. And then you update the elevations of the topography as the combination of the stream power erosion plus some rate of tectonic uplift. So if that rate of tectonic uplift is bigger than the stream power erosion, the elevation of the surface will go up. If it's smaller, the elevation of the surface will go down. And then you do this over some time interval dt. So this is like, I think it'll be 2 years time at which it calculates the new topography each time. If you play around with the value of dt, for instance, in the equation, you can also make it blow up. So yeah, you probably don't need to do that. Then there's a couple things here where it just checks to make sure there's no negative elevations, and that the elevation of the outlet, so where the river hits the right side of the model, is set equal to the same value it started with. So it doesn't go up. It always stays at a constant elevation. So that's updating topography, and then maybe not the big daddy, but one of the other things we have to do is this is going to produce plots of this stream power erosion, like river channel profile over time. It does it as like an animation. So if everything works as I hope, it should be that like you can run this in Jupyter Lab from Binder or CSC, and you should see an animation of this river channel profile eroding in the window. I've tested that pretty extensively, and that should be the case. But you know, things don't always go the way that I hope. But this update figure function is then what updates the plot. So each time it calculates a new, each time it's told to update the plot, which is not actually as often as it updates the topography, it will then update the animation that you're watching. So you'll see how that works when you run it. But anything having to do with updating plots is going to happen in this update figure function. I say that because you're going to have to modify this one a little bit in problem number 2. There's a spot down here that says add stuff to update second subplot here. You're going to have to add stuff to update the second subplot there. So again, you can take a look, read through it. It's going to be a little confusing because there's a lot of functions and there's a lot of things that are passed to the functions. But the idea is pretty simple. All it does is update the plot. Because the plot changes with time, it just updates what you're looking at. And then the last one is the stream power function, and that basically just allows you to call one function to do everything in this stream power law model that we're going to be working with. I won't go through this in detail, but I would suggest that you just look through line by line to make sure that you kind of understand what is happening. It calls a lot of the functions that are defined above, like you can see here's init topography, here's drainage area, and other things like that. The way animations work with matplotlib is you first create the plot, and then you do things like call this update figure to update the plot. So you'll see here actually that this is the place where the plot window or the plot is actually created, and then it's just updated in the other function. When it comes your turn to add a second subplot, you're going to have to add something here and then add something to tell it how to update in the other function. And that's, I think, relatively, at least it's explained, I think, relatively clearly in the instructions for how to do this. And then there's this nasty thing down here, this matplotlib animation function that looks pretty ugly, but this is what handles all the updating of the plot window. And yeah, I'm going to try to put a good number of hints up on the exercise page for this week so that many of these common things that are going to come up get addressed there. But if you have problems, post them in Slack. That's the easiest place for me to look so that I can then know what I can put onto the exercise hints section of the exercise page. And yeah, with that in mind, just before you post in Slack, you should just double check the exercise hints because they'll probably be continually evolving over the next few days at least. Okay, so just spending another minute or two here. Problem 2 is where we start, like the code all gets set up in problem 1. Problem 2 is where you start using it. And the first part, all you do is you just run the code that you've produced above, and it should produce an animation in the window or in the Jupyter Lab that you see when you run that code. So yeah, that should be essentially all you have to do is just run the stream power function here, which literally means you just run stream power with a couple parentheses, and that should be the only thing you have to put there. That will then make a plot, and then there's some questions about the plot that you can answer below that. Part 2 is where you add a subplot. So we're going to have one with the channel profile, and we're going to add another one that shows the erosion rate through time. as the subplot beneath it. It looks like this. So here's the channel profile after 100,000 years. It looks kind of steep and straight, but it will get more curved over time. And then here's the river erosion rate plotted underneath it. And in this case, the landscape is being uplifted at 1 millimeter a year, and the erosion rate in these sections is basically exactly balancing that uplift. That's not always the case, but that's just how it works with this first problem. So the code will produce this top plot to begin with, and then you're going to have to add a subplot for the lower one. And again, then there's a couple questions. I guess maybe not here, but in the next part. Part 3, then, you just play around. If the code's all working at that point, you just play around with a couple parameters to look at the effect of the different initial topography options. The first one's flat, the second one is like a plateau, and the third one is a constant slope. And you can just look at how the stream channel erodes and varies over time, like how its shape changes over time. That should be pretty straightforward when you get to this part. And there's a few questions at the end, and that should be that. So I think it's a little bit daunting in the sense that the code is more complicated this week. But in terms of what you have to do, I don't think it's as demanding in terms of the code that you have to write. It's just more that it'll take a little time to kind of understand how the code works. And I've tried to make it pretty clear and like putting lots of comments in the code and breaking it into functions so that it's a little bit easier to understand. If all this stuff was just one long code, believe me, it's not as easy to understand what it does. Are there some questions or concerns at this point? How have you guys been feeling about the coding stuff for the past few exercises? Do you feel like you kind of get it eventually, or not really? I see some kind of like not convincing faces. So, I mean, of course, like the thing that could be frustrating is if it gets to the point where you're not understanding anything and you're just running the code just to try to finish the exercise. Like that's not great. And this might be, I think this is probably the most complicated code that we'll deal with. If I can give you some general advice about it, the thought is just look at it line by line and don't try not to look at one of these functions and just say, well, this is too complicated. There's no way I can understand this. Because what each line does, in most cases, is actually not that complicated. But if you look at the whole thing, I can easily see even myself getting a little bit overwhelmed with this is just looks nasty. And the other thing is that certainly don't hesitate to ask questions if you have questions about what the code's supposed to do, how some of the functions are set up or things like that, why some things happen the way they do. I'm not convinced that breaking this into functions was a good idea. Last time I had this one kind of long code, but the problem was I think people didn't understand anything of what the code did because it was just all one continuous thing, and I think most people gave up after about 10 lines. Breaking it into functions is a little bit nicer because at least it's like you can try to say, okay, I'll just understand this bit. And if you understand that, then you can move to the next one. And I hope in that way that you'll understand a little bit more of what it's doing. But yeah, we'll see. So what I'm going to do for the moment is, since there's some sections of the code where I've just asked you to kind of read through and get a sense of what's going on, while I fix a couple typos, I will make the current version of exercise 4, I won't make the GitHub Classroom link live, but I'll make it so that you can go to the exercise 4 and just take a look at it and read through yourself. And then it might take me 10 minutes or so to fix the couple typos and update the exercise and add the GitHub Classroom link and stuff. So I'll get started doing that, and you can look through here. If there aren't any questions at this point, then I think maybe that's a good way to go.